let's look at another problem involving mathematical induction, this time involving factorials and summations. So we're given this question to find or to use mathematical induction to prove that this summation, all right, 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial all the way to n times n factorial is going to be able to be simplified to be n plus 1 factorial minus 1, where n is a set of an element of the set of positive integers. Another way that we could write this using summation notation is to prove the summation from 1 to n of r factorial is going to be n plus 1 factorial minus 1. And you could use an I over here or an S, right? You could use different variables, but we're saying that we're going to start at 1 and stop at n, right? Where r happens to be my counter. So our process, we consider the basis step. So if n equals 1, because our first positive integer is 1. If n equals 1, then we have 1 times 1 factorial, right, which is 1 plus 1 factorial minus 1, right, that both of these equals 1, so therefore true for n equals 1. All right, so we're true for our first case. Next, we're going to assume that we are true for n equals k. So therefore, assume that the summation, I'll use an I this time, from I equals 1 to k of I times I factorial is going to be equal to k plus 1 factorial minus 1, where k is some positive integer. So we're going to assume that this is true. All right, that's our inductive hypothesis. After our inductive hypothesis, we're going to consider n equals k plus 1. Okay, so if we consider n equals k plus 1, what we're going to have then is we're going to have 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus going on to n times n factorial. Let's rewrite that factorial a little bit better. And then plus, all right, now we're going to be at n plus 1 times n plus 1 factorial. So that's our case. Well, what do we know? We know that all of this piece was our inductive hypothesis. So we know that we're going to be equal to, based on our inductive hypothesis, and in this case we're going to be using k's because we're working with k's. So let's make sure that we make that adjustment. Very important. Okay, a common mistake to work with n when we're talking about n equals k or k plus 1. So we got that in there. So our first piece we know is our inductive hypothesis. So we're going to have k plus 1 factorial minus 1 and then plus k plus 1 times k plus 1 factorial. Okay. If this is the case, we can look at this. We see, hey, I've got a k plus 1 factorial for two terms here, that I could say that this is k plus 1 factorial times 1 plus k plus 1 and then minus 1, right? That I still have this minus 1 term that needs to stick around. Okay. Now, if I consider this, this is really then k plus 1 factorial times k plus 2 minus 1. All right? And if I rearrange that further, then that's really k plus 2 factorial minus 1. So therefore, we are true when n equals k plus 1. Right? Because if n is going to be k plus 1 instead of k, we're going to have k plus 2 factorial minus 1, k plus 1 plus 1, which is true. So now that we've gotten all our work done and situated, we can come to our final statement. So because, right, our proposition is true for n equals 1, and when our proposition is true for n equals k, it follows that our proposition is true for n equals k plus 1 by the principle of mathematical induction. Our proposition is true for all n. Let's write it like this because it's going to be harder for me to write. For all, let's put this just for the space. All right, for all n in our set of positive integers. And that's our conclusion. So, quick recap. We had our inductive statement, our inductive hypothesis. We considered the first case, our basis. We assumed true for n equals k, our inductive hypothesis. We considered what happens when n equals k plus 1. And in considering what happens when n equals k plus 1, we used our inductive hypothesis. And just so that people don't make the mistake here, right, let's say that all of this, which was the inductive hypothesis, was for this first part. All right, and then we did the mathematics, and it followed that when our inductive hypothesis was true, our subsequent case was also going to be true. So our proposition being true for the first case and our inductive hypothesis being true provides that our subsequent case is also true. Then by mathematical induction, our proposition must be true for all of our values of n, the infinite set. Okay. So another example of mathematical induction. Thank you very much for your time.